I would like actually to convey you some of our most recent investigations devoted to understand and to address what is actually a quite substantial reconstruction of the electronic band structure, which occurs as a function of temperature in these titled Dirac materials. And let me first of all try to briefly introduce the topic of my presentation, mainly with the goal to set the stage for the motivation of our most recent investigations. And I would like to start with somehow from a broad perspective by pointing out that topological materials in general raised quite a bit of interest recently, both experimentally and theoretically, because they allows investigating novel quasi-particles like Dirac and Weyl states, as well as the most elusive Majorana fermions as well. The title materials, which will be the focus of these talks, belongs to this family of topological materials, and they also additionally trigger the attention of the community because they provide an arena in order to address the interplay of magnetism and topology and topological state in particular. So let me try to go straight to the materials which are of interest today. And first of all, I would like to share with you the electronic structure as imaged by ARPES technique. In fact, you can recognize the presence of so-called Dirac cones, which indeed are also guessed by the spin orbit coupling, so that the Fermi level moves into the lower Dirac cone itself. There's also another interesting property here, that the Dirac cone turns out to be anisotropic, which might be of interest when designing novel electronic devices where electrons may propagate differently from one direction to the other. Now, what I already anticipated, these materials are also of interest because they are characterized by a magnetically ordered state. In fact, particularly the calcium manganese bismuth compound, which will be the focus of this presentation, are characterized by a so-called C-type antiferromagnetic order, which occurs slightly below room temperature, with an onset temperature, a near temperature below room temperature, around 270, 80 degree Kelvin. Now, the crystallographic structure is a layer-like structure. The easy axis is the C-axis, so orthogonal to the layers AB plane. There are actually these intralayer manganese bismuth layers which sandwich, so to say, these intercalated bismuth square nets. And the magnetic moments of the manganese ions, antiferromagnetically ordered, align preferentially indeed along the easy C-axis. Now, if we go to the typical characterization properties, like the temperature dependence of the transport properties of the resistivity, we observe an overall metallic-like behavior of the resistivity, which is decreasing as a function of temperature for decreasing temperature. But what is also of interest is that below about 100 degree Kelvin, there's an additional anomaly in the DC resistivity. There's a bump-like feature. One can observe that if you call the onset of that anomaly in the transport properties Ts, that temperature, that onset temperature, shifts to higher temperature upon sodium doping. And even the size, so the shape of the anomaly itself, of this bump-like feature in the transport properties, gets stronger and more robust upon sodium doping. Now, this was rather puzzling, and the origin of this additional transition within the antiferromagnetically ordered state was yet poorly understood. And it was conjectured initially that this could be due to some kind of collective state, charge or spin density wave, In fact, as typical in two-dimensional layer-like materials, you might have some kind of Fermi instability driven by a Fermi surface nesting. This might lead indeed to a partial gapping of the Fermi surface, which may originate also or give rise to this bump-like anomaly in the transport properties, as observed in some two-dimensional charge density wave materials. Now, these collective state origin, so to say, for this anomaly was very much debated, because in the specific heat at TS, you don't see any anomaly at all. From the ARPA's point of view, there's no indication for a band folding in the electronic structure. And also, there's no indication from X-ray experiment for lattice instability, for some kind of lattice distortion occurring at the TS transition. So the possibility or the scenario based on a density wave collective ground state as origin for this anomaly is rather unlikely. And it was proposed alternatively that this could originate from some kind of spin reorientation occurring within the antiferromagnetically altered state. So this was somehow the initial point of our work. We were motivated to shed light on the origin, the consequences and implication of this anomaly in the transport properties in these Dirac materials. So we approached basically the problem from two experimental point of view. First of all, from the perspective of the optical properties, which indeed allows you discussing and investigating the charge dynamics, so via the absorption spectrum, and therefore you have, from that perspective, some insight into the electronic structure itself, but also from the magnetic torque experiment, which is very sensitive to the magnetic state and to the magnetic response of the materials itself. And in order to perform a link to connect these independent experimental investigations, we then perform band structure calculations based on the density functional theory approach. So let me start by discussing the optical experiment. So what we measured is initially the optical reflectivity. The optical reflectivity can be measured over a very broad spectral range, which extend over several decades, an order of magnitude in photon energies. So on a continuum of energies from the far infrared to the ultraviolet as a function of temperature. What we observe as far as the measured quantity is concerned is the typical metallic-like behavior of the optical reflectivity. You see here a plasma edge features, the reflectivity rises and then goes towards total reflection for frequency going towards zero. This is the typical metallic fingerprint, which is indeed preserved when you start to lower the temperature towards TS. So you see that these features are somehow more pronounced. You have a much sharper plasma edge behavior and the plasma edge itself as an onset indicated by the arrow here. Now, this is what happened above TS, so it's a typical metallic-like behavior, so to say. But when we go below TS, so we cross the onset temperature giving rise to this anomaly in the transport properties, we observe that the reflectivity change raises substantially, remaining, however, metallic. So we see here that at low temperature, there's a depletion in the measured reflectivity in the mid-infrared spectral range, so that on the high frequency tail, you have here a broad bump overlap to the plasma edge feature. And then on the low frequency tail of this depletion here, the reflectivity takes off again, merging towards total reflection for frequency going towards zero, indicating that the material remains actually metallic. There's a residual metallicity occurring also here at low frequency. This is consistent with the overall metallic behavior of the DC transport properties. So already the measured reflectivity, which is the measured quantity in our optical experiment, indicate that there must be an impact on the electronic structure and therefore on the absorption spectrum caused by this transition characterized by that bump-like feature in the DC transport properties. In order to better address what is going on from an electronic point of view, one can look to the absorption spectrum. So when you measure the optical reflectivity over such a broad spectral range, which actually in our experiment extend all the way up to the UV, you can then, you have then the prerequisite in order to perform reliable Kramers-Kronig transformations, which allows you then to have access to all optical functions, for instance, like the real part of the optical conductivity, which is shown here for the pristine compound in the spectral range of about half electron volt from the Fermi level. So basically, I'm addressing here low energy scale close to the Fermi level, which are of relevance for the transport properties as well as deep into the electronic structure. And we observe here that there are two main features, which I like to emphasize for the time being. There's a zero energy mode. It's a kind of Drude-like resonance, which gets narrow with decreasing temperature. And then we have these very strong mid-infrared absorptions here, which gets temperature dependent at and particularly below TS, which is for these materials just above 60 degree Kelvin. And in fact, we see that this feature slightly moves somehow to higher frequency, but particularly it gets very, very broad upon decreasing the temperature below TS. Before going any further, I would like to emphasize another interesting fingerprints. Let me subtract artificially the Drude-like resonance from the measured spectra. This is shown here for the spectra at 50 Kelvin. And what I'm left is shown here in the inset is just the purely mid-infrared feature. So basically the interband, the first interband contribution to the absorption spectrum. And what we observe is that on the low frequency tail of this mid-infrared feature, there's a clear linear frequency dependence of the optical conductivity, which is the typical fingerprints already established many times in the past for Dirac materials. It indicates that these absorptions involve actually excitations occurring between the Dirac cones. And this has been seen, as I said, in many Dirac-like materials, and the fact that this linear frequency dependence cut the frequency axis here at finite frequency is an indication for the gapped nature of the Dirac cones themselves in the electronic structure of these materials. Now, the feature that I emphasize, I highlighted here, are very common for all materials which we have investigated, also for the sodium doped compound. Sodium, by the way, is a kind of whole doping of the material. So it means that the Fermi level or the chemical potential actually is lower into the lower Dirac cone itself. So we see here that the feature I was pointing out for the pristine compound are here even more distinct. You have clearly this Drude-like resonance narrowing as a function of temperature. When you decrease temperature, you see this mid-infrared feature with a low frequency tail characterized by a linear frequency dependence crossing the energy axis at finite frequency. And then what I said before, being a broadening of this mid-infrared feature when you go below TS, if for the sodium compound turns out to be actually the consequence of a split into two single excitation of that mid-infrared absorptions, which occur at and below TS as well. At higher frequencies, this is shown here in the inset, we observe additional absorptions, which turns out to be temperature independent and very common for all investigated materials. These are due to electronic interband transition from state well within the electronic structure, so far away from the Fermi level to state just at the Fermi level or above it. But I will not discuss this in further detail later on. Let me focus my attention now on these far and mid-infrared spectral range that's shown here, So the optical spectra indicate that the transition at TS, as observed with the transport properties, has an important impact on the electronic properties of these materials at these energy scales, as indicated by the charge dynamics. So there must be actually a reconstruction of the electronic band structure occurring at this transition, as I said, at TS. And what we also observe here, that all this is possible because of an important reshuffling of spectral weight. And let me try to elaborate on this typical optical concept. There is a common quantity in optics to integrate the real part of the optical conductivity from 0 up to a cutoff frequency. And this model-independent quantity describes basically the number of charge carriers normalized by their effective mass, which are involved in the absorption processes up to these cutoff frequencies. Now, if we look at how this quantity looks like, for instance, for the pristine compound, here at this relevant temperature, so above TS, at TS, and just below it, so we see that there's an important redistribution or reshuffling of spectral weight occurring at low frequency, but in fact, all the spectral weight is fully recovered at all temperature at about 1 electron volt. In fact, you expect that when this cutoff frequency tends to infinity, that this quantity should merge into a constant temperature independent value, which indicate that you satisfy the optical F-sum rule. And this is already the case at energy scale of about 1 electron volt or so. But there's an important reshuffling of spectral weight at low energy scale. And in order to better emphasize the temperature dependence of the spectral weight redistribution, I will consider now the ratio of this integrated spectral weight at temperature below TS, which is right at 50 Kelvin for this compound, and normalized by the same quantity at TS itself. And this is what we get for this specific material, but similar results were obtained also for the sodium-doped composition. So when this ratio goes above 1, it means that you have a shifts of spectral weight from high to low frequency, in this case piling up and accumulating into the effective metallic contribution to the optical conductivity, this narrow Drude resonance. But when this ratio goes below 1, it means that there's a removal of spectral weight in the spectral range, which is then reshuffled at higher energy scale. And this is possibly due to a partial gapping, indeed, of the Fermi surface itself, so to some erosion of the density of state at the Fermi level. Actually, it's possible to show that the depth here of this spectral weight ratio is also a measurement of the fraction of the Fermi surface, which is apparently gapped by this transition occurring at TS. And we were able to show, I may possibly describe this in the discussion later, that this is totally consistent with the estimation of that partial gapping of the Fermi surface that you can get from the size of the anomaly in the bump-like feature of the DC transport properties. Let me also mention in this regard that by applying a rather phenomenological Drude-like or the Drude-Lorentz phenomenological approach, we can also show that the removed spectral weight here is actually coming from the high frequency tail of the Drude-like resonance, which then is reshuffled to higher frequencies. Now, we can certainly say, as you see here, that the transition at TS induce a very important reshuffling of spectral weight because of this relevant and substantial reconstruction of the electronic band structure. Now, the question is where this comes from, what could be the origin for that? And quite instrumental to answer this question was the magnetic torque experiment, which we also performed on the same compound. So basically, we measure the magnetic torque by rotating the magnetic field by an angle theta with respect to the EZC axis. And we did this measurement at several temperatures. So what you see here for one composition is the measured magnetic torque as a function of this angle theta at two temperatures. So above Ts for these materials and below it. Now, in general, this kind of response can be described by these phenomenological equations. The first term here with the coefficient A is the sinus 2 theta term, correspond to the expected response in the magnetic torque due to the antiferromagnetically ordered state. And indeed, above Ts, this function does a very good job in fitting the experimental results as expected. But we observe that below Ts, this first term does not fit very well the experimental data. There's a substantial deviation indeed. And this can be accounted for by adding a second term in this phenomenological equation with this B coefficient. It's a sinus theta term. And this would be a term which comes in the magnetic torque when an additional ferromagnetic-like contribution to the magnetic state occurs and happens in this system. Now, it seems that when crossing this transition at Ts, an additional ferromagnetic component in the magnetically ordered state below Ts in these materials develops. And we can obviously repeat this experiment at all temperature for all composition. So we can extract the temperature dependence of the A and B coefficient. And what we observe, this is summarized here for all investigated compositions. So you see that the A coefficient is pretty large and is negative, and there's a clear temperature dependence. The temperature dependence is fully consistent with the expectation due to the dominating antiferromagnetic order in this system. We see that the B coefficient is smaller than A. It's always positive. It's slightly different from 0 at higher temperature, but it clearly takes off and gets very robust at and below Ts. And this indicates that there must be an additional ferromagnetic contribution to the magnetically ordered state of this system. And we propose that this is actually due to a spin canting of the magnetic moment of the manganese within this layer-like structure. In fact, from this analysis, we can also establish the corresponding phase shift in this phenomenological approach. It turns out that C is actually equal to 0, but D, as phase shift of this additional contribution here, is of the order of 10 degrees. So it means that below Ts, there's clearly a spin-canted antiferromagnetic order in this system for about, with an angle of about 10 degrees, which lead to an effective ferromagnetic-like projection of the manganese magnetic moment within the AB plane of these materials. And these results were also confirmed by an additional experiment where the magnetic torque was measured at fixed angles, but by sweeping the magnetic field itself. And all these data are consistent with this spin canting scenario. Now, in order to connect these results, which probe, so to say, the magnetic response of the system with the charge dynamics that I show you initially in this presentation, we performed band structure calculation within the density functional theory approach. So what you see here on your left is the calculation without spin canting, and on your right, you see here the calculation of the band structure by taking into account such a spin canting of 10 degrees from the EZC axis. Now, I don't have time to go into all the full details of this calculation, which is very complex indeed. I like to emphasize or to highlight that the relevant orbitals shaping the Fermi surface is actually the PZ orbital of the intercalated bismuth square net, in this layer-like structure, which is the orbital, which is very much affected when you switch on the spin canting. In fact, by switching on the spin canting, such as PZ orbital gets splitted across the Fermi level, and this has important implications. First of all, there's an erosion of the density of state as far as the PZ orbital is concerned, which is quite substantially suppressed at the Fermi level. This accounts per se for the removal of spectral weight seen in the optical spectra from the Drude component, so from the effective metallic contribution to the charge dynamics, and therefore indicates a partial capping of the Fermi surface. The splitting that we observe here in the band structure calculation also leads to additional possibility for interband transition. And in fact, with the Kubo formula, you can extract from this band structure calculation the interband contribution of the real part of the optical conductivity. So without spin canting, you have as dominating feature these mid-infrared absorptions right at the energy scale observed experimentally. And interestingly enough, when you switch on the spin canting as we proposed, and because of this additional interband transition, that absorption split at least into two single excitation, which was also quite clearly recognized, particularly in the sodium-doped tidal compounds. So approaching the conclusion of my talk, since I'm slowly running out of time, we can certainly say that these, or we would like to propose and to convey the message that this transition, which occurs as a bump-like anomaly in the DC transport properties at TS, we propose that it is due to spin canting. So this has important consequences and implication on the electronic structure, which gets very much reconstructed below TS, so that removal and a reshuffling of spectral weight occurs in the charge dynamics, as observed in the real part of the optical conductivity, and which is substantially, or let's say in the end, is also the origin, so to say, for this anomaly in the DC transport properties themselves. And this might have important implication because the onset of spin canting may also indicate a broken time reversal symmetry, and therefore these materials could be possibly a candidate even for the realization of Weyl state, which is still a very much debated aspect of this family of Dirac materials. More details about our work, you can get them by at these two recent publications of my groups. And in the end, allow me please to acknowledge the great work of my team, particularly my PhD student, Matteo Corasaniti, by the way, a former student at La Sapienza, my present postdoc, Rune Young. Then we got a beautiful spaceman from Sidomir Petrovic at the Brookhaven National Lab, and we enjoy a great collaboration with two groups based at the Institute of Physics of the Chinese Academy of Science in Beijing for the magnetic torque and the DFT, magnetic torque experiment and the DFT band structure calculation. Last but not least, I would like to acknowledge the great financial support of our agencies, funding agencies in Switzerland. And with that, thank you very much for your kind attention.